Okay, I think that's time to start the last session of this workshop. And the first speaker is Maxime Jacquet. Yes, so please.
Hi everyone. So I will be telling you about Polariton hydrodynamics for analog gravity. And today really I'm only the voice of a larger group. And so I'm working for Alberto Amo, Quentin Glorieux, and Elisabeth Jacobino in Paris. And the work that I'm going to present is done in close collaboration with Jacopo Caruso. And really, all of the simulations and so on that I'm going to show today have been done by Yuhao Liu, who is doing his master's project with us. Okay, so Polaritons, I think, is one of the systems which we haven't heard of during this meeting so far, but Jeff has mentioned them yesterday. And the reasons why we're interested in doing analog gravity with Polaritons is that simply we know how to observe quantum effects very well in these systems. And also by changing the cavity sometimes, or by changing the beam with which we pump the cavity, we can go from one-dimensional to two-dimensional systems in spatial dimensions. And that's very interesting to us because we can therefore use this platform with very little efforts and go from different physical settings. Also, I would like to highlight this experiment that was done in 2015 in the group of Alberto Amo and Jacqueline Bloch, and it was led by Nguyen. And in that experiment, they demonstrated how to make a horizon in a polariton. But then this experiment wasn't followed up by any sort of scattering observation. And I think that throughout this talk, it will become clear why that is. And also, one running theme of this presentation is that polaritons or the Polariton system can sort of very easily be compared with the Bose-Einstein condensates, the atomic Bose-Einstein condensates. This comparison, of course, has its limits, hence the red question mark, and this will be something which I come back to during the presentation. All right, so today I want to first tell you about polaritons in microcavities. So I think polaritons are not very famous in analog gravity, so I will take some time to tell you what's actually going on in these systems. So what we have is a semiconductor. It's a quantum well made of helium gallium arsenide, for example, in our setups. And what we do is that we pump this semiconductor, these quantum wells, with a laser beam, a coherent laser beam. That can be continuous wave excitation, or it can also be pulsed. Today I will talk only about continuous wave excitation. When the semiconductor is pumped by the laser beam, the light couples with a particle or a quasi-particle that's already living in the quantum wells, that is holes and electron pair holes. And via this coupling, we create what are called polaritons. And in that sense, polaritons are really mixed exciton-photon states. So they inherit some properties from both of their parent particles. So for example, from photons, they can be confined inside a cavity. So we put this semiconductor layer, these quantum waves, in between two distributed Bragg mirrors, which confine the photons inside the cavity. And when the photon exceeds the cavity, we can observe it very easily in real as well as in reciprocal space, which allows us to really make all sorts of measurements, including phase via interferometry. And what's nice is that these photons, as they interact with the excitons and from the polaritons, really they give rise to a very strong nonlinear refractive index. So there is some K3 nonlinearity inside the cavity in the semiconductor. And therefore, polaritons are bosons that interact with one another. So when we pump the cavity with a certain photon, it acquires a sort of effective mass. And as it interacts with the exciton in the strong coupling regime, polariton branches will form. And as a function of the frequency, so how far detuned we were initially, we will get more or less photonic or excitonic content in our polaritons. And in the experiments that I'm going to talk about today, and the simulations I'm going to talk about today, we are mostly working with the lower Polariton branch. All right, so this is this branch here. That's the result of light and matter interactions. And what's very interesting about Polaritons is that if you write out their wave function, you find out that it looks a bit like a Gauss-Pitevsky equation that we know from the Bose-Einstein condensate. So here is one first contact point. It has these two additional terms here, which represents the fact that really this system is driven dissipative. As I said, we have light that enters the cavity and that then exits the cavity. So the system is not contained, it's a driven dissipative system. And one very interesting thing that we can do is that we can make those polaritons behave like fluids. So we can study the hydrodynamics of polaritons inside the cavity. And the way we do this is usually by studying the Gauss-Pitevsky equation in a linearized way. So as we have seen earlier today and in David's talk and also yesterday, for example, in Ted's talk, we basically study small excitations, which we call Bogoliubov excitations, on top of the Polariton fluid. And what we find when we do this linearizing game is that Bogoliubov excitations follow a wave equation with a certain dispersion. And that's the dispersion I plot here as a function of the flow speed of the polaritons inside the cavity. If the polaritons go slower than the speed of sound in the cavity, then this is what the dispersion relation looks like with positive frequency branches and negative frequency branches. If now the Polariton flow is made to go at supersonic speeds, there will be a Doppler effect whereby some branches change shape, and in particular, this red branch here is pulled up to positive frequencies. This is all very, very well explained in Jacopo's review of modern physics, and I really encourage you to have a look at it. So one thing that happens with the polaritons when they are going subsonically is that we can make them behave like superfluids. So in fact, the polariton density, which is proportional to the square of the wave function, has a bistable relation to the intensity with which we pump the cavity. And if we work in this regime here of the bistability at the upper left, we can get superfluidity. And this is what is shown in these diagrams here. So if we look on the left-hand side, what we see is really an image of the cavity. So we simply collect the light that's coming out of the cavity. We pump the cavity with a Gaussian beam, hence the general shape here. And this beam has an incoming angle whereby the flow of polaritons has a preferred direction from the right to the left. And it impinges on a small defect here at the center of the image. And when the power is low, so when we are at the bottom of this curve here, we see that, well, there are some undulations that form before the defect, so because of reflections on the defect. But then if we increase the power and come to this point here in the bistability curve, what we see is that the fringes, really the undulations disappear. So there is no more undulation no more partial reflection at the defect, which means that we have obtained superfluidity. And this is when the flow speed is subsonic. So this is, for example, shown in, so these experiments here, they are taken from a PhD thesis from the group written in 2012, but there is also some interesting explanation of this in a recent review that people in the group have written. Okay, so if we have polaritons that behave as a superfluid, we can really think of them as a fluid of light, and this can be useful for analog gravity. I don't want to bore you out with the maths that have been shown to us already many times during the meeting, but I want to point out, to highlight a paper here which was written by the group in Clermont-Ferrand by Solnishkov and Malpuech. And in 2011, what they realized is that really these polaritons, they naturally exhibit an event horizon for the sound waves. Here, this is very well explained. So we have the density of polaritons that decreases as we go away from the center of the pump. So we pump with a Gaussian beam, for example, and as we go away from the center of the pump, the polariton density decreases. The phase of the, okay, sorry. And the speed of sound is proportional to the polariton density, so it decreases with the polariton density. On the other hand, the flow velocity of the polaritons, which is shown in red dashed here, is proportional to the phase of the polaritons. And roughly speaking, it increases when the polariton density decreases. So naturally, as we go away from the center of the pump, there will come a point at which the flow velocity of the polaritons equals the speed of sound in the medium. And after that, the flow velocity of the polaritons will be supersonic. So naturally, we have horizons that arise in polariton systems. So this is a very useful tool that we can use to try and observe effects like that. And of course, the metric that I write here can be generalized to higher dimensions. And for example, we could obtain a vortex flow like Silke's experiments. Okay, but what I want to talk about today is really one-dimensional flows. So again, we have our sample with the quantum wells here shown in yellow in the middle. And I pumped the sample with a Gaussian pump, with a Gaussian beam. This beam has a small angle, a small k, whereby the flow of the polaritons is in this preferred direction along increasing y. And here again, I plot the flow velocity of the polariton in blue and the speed of sound in orange. And on the right-hand side, I zoom simply around the horizon or around this crossing point. And we see that this crossing point is not very sharp. I mean, really the flow velocity of the polaritons, it doesn't increase very, very fast at this crossing point, at this horizon. And there is this idea that the sort of the rate of change of the flow velocity at the horizon gives you the temperature of Hawking emission, or in other words, the intensity of the signal. So what this tells us is that if we naturally let the polariton density decrease and we see the related increase in the flow velocity from sub to supersonic, we will not get a very high Hawking temperature. And this is basically what the group of Jacopo Caruso calculated in 2012 in a paper. I think most of the work was done by Dario Gerace at the time. And so what they suggest is to use this polariton wire, but to etch a small defect in the wire on perpendicular to the wire, which will very sharply modulate the density of polaritons. So here I plot the density of polaritons. And what do we see? We have a Gaussian pump that's centered at a certain position. And a bit away from the center of the pump, we have a defect. And as we see, the defect really strikingly modifies the shape of the polariton density. And this is very well reflected in the velocities. So again, we have the flow velocity of the polariton in blue and the velocity of sound in orange. And what we see is that at the point where the defect is situated, there is a sharp, very sharp increase in the flow velocity of the polaritons. I zoom in on the right-hand side, and we see that we have a much better gradient now than we had before. So this idea by Jacopo and Dario to etch a defect here seems to be working very well. And this is the experiment that was run in the group of Jacqueline Bleur and Alberto Amo. And at the time, they measured really a subsonic and a supersonic flow here, and they could prove that they had a horizon. So why did they not observe really the scattering of waves then at this horizon? And that's a question that I really don't have a real answer to, but I think I have a hint. And so I'm going to show you some simulations of the spontaneous emission at this horizon. So this simulation is run, so this is a numerical simulation. It's a truncated Wigner approximation. The code was written by someone in Jacopo's group, and it's run here for us by Yuhao. And again, we use this idea from Jacopo and collaborators to measure the density correlations across the horizon. So what does that mean? Well, as we've heard many times today, we have this dispersion relation. On the left-hand side of the horizon here. On the left-hand side of the horizon, we have a subsonic flow. On the right-hand side, we have a supersonic flow. And so we will have scattering of incoming waves into outgoing waves. And this was very well explained by Mathieu. So I'm just going to jump to the conclusions. What we are interested in is this channel from U out to D2 out. Okay, U out is a positive norm mode that propagates in the upstream region against the flow, whereas D2 out is a negative norm mode which propagates in the downstream channel together with the flow. So both of them propagate away from the horizon in their respective region. And they have a given group velocity, and they will carry some energy, and this is this energy that we see the correlations of here. So of course, they are phonons, and what we see here are density fluctuations. That's how we can understand phonons in a sense. And we see a small trace here, this blue trace, which seems to correspond to this U out, D2 out channel. And you also see some dashed straight lines, and these dashed straight lines are the sort of predictions that you could make for the various features of emission from the horizon if you did not take dispersion into account. And if you do that, you realize that really a dispersionless model doesn't really tell you much about the experiment that you're trying to run. So what you have to do is really to take dispersion into account, and then you get a much better agreement between your theory curve and the numerical simulations that you obtain. Now, like Mathieu did, and also like Jeff did in his experiment, we would like to know what really is the signal that we are going to see. So what we do is that we run along the feature that's of interest, and we look at the averaged correlations that we get. And this is the shape we get. So again, it resembles very much what Mathieu calculated for the Bose-Einstein condensates in atoms. And the interesting features here are the fact that this is relatively wide. In fact, it's wider than if there were no dispersion. And also there is some asymmetry, and this asymmetry can be understood first from the dispersion and also from those undulations that we see here. So looking at Mathieu's plot, we see that there are some undulations in the figure, in the traces of correlations. And we see the same undulations here. And I don't really understand them very well, but if you ask Nicolas Pavlov what he thinks about them, he will tell you that they look like airy figures. I'm not sure they really have to do with dispersion per se, but he would say that they have to do with airy figures. Two important points here. The first thing is that we have a driven dissipative system, and Renaud, among the many things that he showed together with collaborators always, was that in a driven dissipative system, there will always be an incoherent bath of phonons in the input state, which means that these incoherent phonons will scatter at the horizon, and they will create some noise into my signal. This is not taken into account in those simulations. Also, in Mathieu's and Nicolas' recent paper, they show that from such a plot, we cannot really infer that there is spontaneous emission. Indeed, if we increase a tiny bit the temperature of the atomic Bose-Einstein condensate, we get a curve which it's difficult to tell whether the points match more the yellow curve or the red curve being for zero temperature, the yellow curve for higher temperature. So it's difficult to tell from such curves that we really have spontaneous emission, both because of the temperature problem and also because of this bath, which is not taken into account. So the proposal that we have is to really use a measure of entanglement to tell what's the entanglement in the system. Okay, thank you very much. And so here I'm switching to a slightly different system because that's what I studied before, but this measure of entanglement that I'm going to talk about today, which is the logarithmic negativity, could be used to assess the entanglement content of the correlations. This is really what I want to tell you about. So again, I have a system in which I have some amount of dispersion. There are various modes that can that can oscillate on either side of a step in the refractive index here. And what I try to see is the amount of correlations that I get as a function of the frequency here when I go upwards in this diagram, and the amount of correlations in between those various modes. In fact, there are more modes in the system, but the main modes are shown here. They are the main players always. And what we see is that as a function of frequency, we have various correlation figures. When we have a horizon, for example, here, we have a very strong correlation between a mode that's propagating away from the horizon and a mode that's propagating inside the horizon. So that's quite good. So what's the entanglement content? We calculate that by the logarithmic negativity, and we find a pretty good relationship between the entanglement content and the correlation coefficient. However, if we plot this relationship between the entanglement content and the correlation coefficient, we find that we don't really have, strictly speaking, linear relationship. In fact, if we now plot exactly the same value on a log-log scale, we see that for low correlation coefficient, the entanglement content can be pretty much anything, from varying over 2 orders of magnitude or something like that. So measuring correlations don't really tell you about entanglement. That's a very important message to take home. So we will need to do both when we want to run such an experiment. We will need to measure the correlations, and we will need to measure the entanglement as well. One doesn't give the other very linearly for any dispersive system. And this is one of the messages that I want you to take home today. So what I wanted to tell you is that really we can set up horizons in polaritons in microcavities, and that these horizons, they will emit by the Hawking effect, and they will emit in pairs. And these pairs, they are correlated and perhaps even entangled. However, there is still a lot of work to be done before we can run such an experiment. The main reason is this number that's hidden here, which is 10 to the -5. That's the intensity of the correlations that we could see, the amplitude of the correlations. That's very low. Jeff will be able to tell us better, but I think that in his experiments, so we are sort of 2 orders of magnitude worse off with our polaritons. However, what we could do is that we could measure them in K-space, as was done, for example, as was proposed in one of Nicolas' papers. We could measure the spontaneous emission in K-space, and we could also stimulate the emission. This was studied by the experiment, where we use this setup, and instead of letting the vacuum scatter on the horizon, we also send a probe, which with a certain amount of energy, and then we could observe the correlations, as was done, for example, in Germain's group in 2016. Another thing that's very interesting, and that was shown by Elisabeth when she gave the first talk on polaritons in a long time, is that we can also go from one-dimensional geometries to two-dimensional geometries. So by going back to a sort of rectangular cavity and giving some orbital angular momentum to our pump, we can create a vortex flow. And this would allow us to study in a polariton system effects such as those that have been seen in Silke's group. We had a very, very nice talk earlier, and this has been one of the main inspirations for the group here, which we will be into. And now I will simply conclude by telling you that last year we had this meeting at the Royal Society, and following on this meeting, there will be a theme issue on analog gravity that will be published by Philosophical Transactions of the Royal Society A. That's going to be published later this month or next month, and so look out for this. I think there is a nice collection of paper in there, and they really are worth reading. Thank you very much.
Thank you very much. So we might have time maybe for one question. So, yes, please, Silke. Cool.
Hi. Sorry, this was
Hi, Silke.
quick. Hi. Sorry, I'm using the headphones now. So first, was a very nice talk. It sounds like a really exciting system.
My headphones.
Sorry, my daughter is next to me. So I have a question. Could you explain to me the one thing which is not so clear to me? How do you know how quantum your system is? Like, you know, in a BEC or in a fluid, it sort of can estimate how big the thermal fluctuations are, and then I can see, well, how much is the thermal fluctuations are suppressed compared to the quantum noise in the system. So where are you in these experiments, and where do you think you will be compared, for example, to BEC experiments?
Okay, yeah, so I don't know really for sure. The first thing is that for sure the spontaneous emission is going to be much weaker. Because here, basically, this is, I mean, he ran a lot of simulations, and really, this is the best that we can get, this 10 to the -5. And so how do we know that we have those quantum fluctuations and not thermal fluctuations at the input? Well, really, I think we cannot really know, and this is precisely because of what was shown in this paper by Jacopo and collaborators. I think there will always be some incoherent quasi-thermal bath of phonons. And these are not really of quantum fluctuation origins, so to say. So there will always be some background noise. And I'm sure Jacopo would have a much better answer to give to this, but this is basically what I can tell you now.
Can I ask one more question? Is it okay to ask one more question?
Please.
So I think if you, in principle also, right, if you have waves in the system, they also carry a mass flux. Do you think you could perhaps, and somehow they would accumulate, could you also see back reaction effects if they would occur in your system?
Well, in the one-dimensional case, I don't really know. In the two-dimensional case, that's really one of the questions which we are trying to look into at the moment. So I don't have a definite answer to give you, but I would think so. The thing is that for us, so if we look at this plot here that I'm highlighting with my mouse, hovering above with my mouse, what we have is a beam with a certain amount of angular momentum that's seen by all the phase jumps in this figure. And the Polaritons, they exist only, I mean, they are subsonic, and we have superfluidity only in the region inside that beam. So we will always be under the sort of the pumping mechanism. And I don't really know how that ties in with what you do in your experiment. But basically, we will be constantly seeding the process with new Polaritons. And we also don't have this drain at the center, not really. Polaritons escape the cavity at all points so we don't really have a drain in the center. So I don't really know exactly how the two systems compare yet. But that's certainly something which we need to look into, and I think we will need to have very long conversations with you to learn more about this.
Sounds like a really interesting, exciting system. So I'm very happy to discuss.
Yes, thank you very much, and we have to thank Maxime and continue. Thank you. So the next speaker is the Wu. So please, if you can unshare your screen, yes.
Did I share my screen already?
Not yet.
I collect. Sorry, I shared my screen. It's not showing up.
No, it worked.
No, it's not there yet.
Yes, now it happened. Now go please full screen. Yeah, works. Great.
Works now?
Yes, please.
Okay, great. First of all, I would like to thank